And hello again, OpenFoamers. Welcome back to our OpenFoam discussion. Today we want to look into calculating the Grashof and Rayleigh number. So we first take a look. Of course, in the last video we were calculating the Prandtl and Nusselt number. For comparison, now we want to take a look at Grashof number. So this is the Grashof number. So the formula is here. Then I can just do this Grashof number. Okay. First thing, it's G times B, G into beta. Grashof equals to G into beta. Okay, so this is the Ts minus T infinity. So solid temperature minus fluid temperature. Ts minus T infinity, or T fluid, D cube, divide by nu squared. So this is Grashof number. If you want to do a conversion from kinematic to dynamic viscosity, all that we have to do is this. We replace this by the mu, and we put density on top, because nu equals to mu over rho, right? So kinematic viscosity equals dynamic viscosity divided by density. So this is what the Grashof number is. And so we need a few pieces of data to start calculating the Grashof number. One is this gravity. Gravity is just 9.81 meter per second square. Okay, meters per second square. And next thing is surface temperature, which is inside our thing. We also need beta, which is the expansion coefficient with respect to temperature. So for clear definition of that, okay, beta over here, according to this website, equals to del del T P. Okay, so minus 1 over rho, partial rho, partial T, and a constant pressure. So this is a constant pressure kind of thing, and this one we will need to calculate again. Looks like some differentiation we need to do based on our polynomials. And next thing we need is our d value equals to 3 over 100 meter, and of course rho, we will need to calculate rho again, and mu we have kind of talked about it before. We have actually already done the dynamic viscosity over here. We just need a value for rho and beta. So this, let's just do a checkbox. This is okay. Oops. This is okay. This is okay. Temperature's okay. And we just need the density values to calculate the Grashof number. So let's take a look at density. It might take a while, but let's take a look at density versus the okay, density versus temperature, and this is it. And then we'll just do the same old trick again that we are doing in the last video. Good thing this formula is pretty easy to reuse. So this is the polynomial fit of density versus temperature for the whole term. You just do the same thing, change to scientific. Let's put it at like 6 decimal places just for the heck of it. It is a polynomial fit to the third power. So first 3 terms I'll just put 0, 0 and 0. Okay, density here. Okay, I will just do this, minus to the cube plus 1.7 10 to the minus 3. That's for the square term. minus 1.39 for the t term, and the constant is 1.36 times 10 to the 3. Okay, so I'll just copy and paste here. Okay, I think instead of naming this, I will just do t squared, t cubed, t4, t5, t6. I think that's easier to identify. Alright, so you have a density of this much, 1054 point something something, so that's the density. Okay, so density is here, density data at 300k, and I'm going to paste the picture. There we go. Rho equals to 1054.2588. Alright, so what I need to do, just copy and paste here. Okay, so I'll put density here. Okay. Of course, you want to do a more efficient way of doing it, you can, but I'll just leave it as that. Okay, density is done. Now we need to look at the beta, the expansion coefficient. For that, we just need to do some slight modification. Alright, good thing this is a polynomial, so the differentiation is pretty easy. Okay, beta, okay, beta. Okay, I forgot to change this. Density. And yeah, this should be the right one. Okay, paste this here. Okay, it's a little tedious, but yeah. Next thing is to do some differentiation. So the t cubed term, you have to times 3, right? Equals to whatever this is. Okay, never mind. I will do this. I'll just delete or paste the zeros in all of them. Okay, so t squared term equals to the t cubed constant times 3. As we bring the power down there, t term, you go to the t squared term, you times 2. Okay, and of course the t term, the constant term, equals to this. Alright, so 2, 3. So you see, you differentiate the constant, it will just be 3 times 3 times 2 and times 1. So that's how we get the beta. That's a good thing. Yeah, again, the differentiation is pretty easy. So we have the value for our beta over here. Okay, this is not beta yet. This is dp or d rho dt. Yeah, that's what it should be, d rho dt. And I'll just paste it down here. Okay, rho partial t at constant pressure at 300 Kelvin is minus 0.8228. Okay, so the beta, now we can do beta, goes minus 1 over rho, and then we just have this. Okay, sorry, it should be a large T, right? Okay, there we go. Okay, so minus 1 over rho times whatever that is. So beta is there. Beta is here, minus 1 over density times this. Okay, so we have this beta. I'll just put this here. Paste as picture. Okay, there we go. We have calculated our beta successfully. Now the Grashof number should be quite trivial to do. Okay, let's just put our beta over here and paste as a value beta. So now let's do the Grashof number. Like I was saying earlier, Grashof number is g into beta. So 9.81 times the beta. So we lock that cell times Ts minus Tf times Ts, which is this surface temperature, minus 300. And we don't lock it because it will change. Okay, Grashof number will change, times d cubed times d. D is the over here, d to the power 3 times rho squared times the density squared. Now that must be divided by viscosity squared. So dynamic viscosity squared here, we divide and we have a nice Grashof number. Oopsie. I think I forgot to lock. Okay, this should lock, this should lock, and this should lock. Okay. Okay, I think yeah, should be good because the Grashof number is changing. Now let's see whether what the Rayleigh number is. Let's see whether this is a turbulent or otherwise kind of a flow. Okay, so let's format it as scientific format. Where's the scientific format? There you go. 1.41 times 10 to the 8. And you just give it more decimal points by clicking on that. Okay, so the biggest Rayleigh number is 1.411 times 10 to the 8. Okay. Okay. Largest Rayleigh number is 1.41 times 10 to the 8. So Rayleigh number equals to Reynolds number, Grashof number times Prandtl number, and that's equals to 1.411 times 10 to the power of 8. Okay, so Grashof times Prandtl, that will give the Rayleigh number, which is good because it's actually below. This is below our threshold, 3E8 for liquids. Okay, oil is water. So this laminar simulation is probably correct. So that's the first part I want to bring across. The Rayleigh number is below the threshold for turbulence, so this is using laminar flow simulation is totally fine, perfect. And we have a correlation between the Rayleigh number, Nusselt number, Prandtl number, and Nusselt number. So this is the plot that we want to generate. Okay, so this is I just label this experimental. Okay, CFD. Right, this is an OpenFoam version. Foam hot sphere in oil. And next thing we want to do is compare that. All right. So I'll have the Rayleigh number. Now paste it here. And the Nusselt number, I will paste it on the right. So the Prandtl number is of course 43 point something. Okay, as long as we calculate that right, should be okay. Okay, so this is the hot sphere in oil case. Oops. So this is the first one. Okay, and now we can use the correlation. Okay, where's the correlation? We want to use this. We want to use this correlation. So, all right, we have 2 plus something. So Nusselt in the correlation is this. Okay, I'll just do it here. Correlation equals 2 plus 0.589 times Rayleigh to the power 1 over 4. Okay, 0.589 times the Rayleigh number to the 1 over 4. Okay. And then I need to divide it by the 1 plus, okay, divide by close bracket and okay, 1. Let's do it to the power of 4 over 9 first. I'll do the outermost bracket, 4 over 9. Okay. So that's 1 plus something plus a Prandtl number expression, power 4 over 9 at the bottom. So 0.469 over Prandtl is the next part. Okay, bracket 0.469 over Prandtl, divide by the Prandtl number, which is here. Okay, that's the next part, and I'll need to put that to a 9 over 16 power. Power 9 over 16. Okay. I just want to double check. This is for yeah. Okay, Rayleigh power to the power 1 over 4 divide by something, the Prandtl number function to the power 1 over 9. 0.469, 0.589 on top. Okay, I'm going to drag it all the way down. Let's see. Obviously, there seems to be a mismatch here. Okay, so it's Nusselt versus Rayleigh number for correlation versus the CFD. Now it looks like the correlation one kind of over predicts the CFD one, but yeah, and the trends kind of differ a little bit. But okay, maybe there's some errors in. I want to check whether there are some errors with the whether what I plot was right and all that. I want to take a look at that, and of course the correlation, did I put in the data right? I want to check whether I did that. But anyway, that's I mean, the gist of it is that you're supposed to compare the data versus a trend plot, which is what I did here. And hopefully I did that right. So I'll probably go and double check to see whether there's some errors and see whether there's really this kind of discrepancy that's going on. Probably due to some meshing problem or maybe some typo somewhere. But that is that. Thanks for watching. Continue more discussion in the next video.